Hello everyone, hope you're doing fine. And as always, if you have not subscribed to my channel, I would humbly request you to subscribe to my channel so that you shall be able to see all the latest engineering videos that I will upload on my channel. Thank you. Okay, all right. The problem with us right now is basically we want to do statically indeterminate airplane floor wing aluminum alloy beam analysis. Okay, so this is a problem for our behavior, and we are trying to make it more complex, and we have slightly edited the data so that this beam will not fail. So we have basically this floor beam. The question is that the loading on the floor beam used in the airplane is shown. Determine the reactions at the supports A and B, and then draw the movement diagrams for the beam. Okay. Moment at C is given as 10 pounds inch, and this moment, if you look at it, it is clockwise. So this and the rectangular section is being given for the beam whose dimensions are being shown to us. So if you look at this beam at A, there is a roller being placed. At point B, there is a fixed support. The roller will give you one reaction. The fixed support will give you three reactions. Then there is a UDL of 3 pounds per inch at acting from D to B. The length is 120 inches. The total length of the beam is 240 inches, and the moment applied at point C is 10 pounds inches. So this is basically the explanation for this problem of ours, and now we shall proceed with the analysis. Okay, so let's start with the problem. This is again a structural based problem, so we shall select it like this. And the element type that we will select for this problem is a beam, because it's a beam analysis 2 node 188. We shall close it down, and then we will go for the material properties. But before going to the material properties, we should be seeing this material, aluminum wrought alloy 60620T6. Its modulus of elasticity is 10 into 10 to the power 3 KSI. Okay, so it will be 10 into 10 to the power 6 pounds per inch square, and it will be yielding. If you look at it, it will be yielding at about 37 KSI. So it means 37,000 pounds per inch square. Okay, it will yield at this value. Okay, so now if we go to the material model, we will ask structural, linear, elastic, isotropic. It will be 10 E6 pounds per inch square. This will be 0.3. You can say it as 0.35 if you want, and we will close it down. We can now basically done the job for material properties. Now we select the section, and the section is basically beam. It's a common section, very common section. As I told you, there are a lot of sections over here. You can select any one of them depending upon your project or problem in hand. We'll select the simplest one as the rectangular one. Okay. And basically for the dimensions, we'll be doing this 3 and this 1. And we'll basically be applying it. So once this has been done, now we will basically go for the modeling of the beam, the aluminum beam of the aeroplane. We'll try to create the key points. We have already seen what will be the dimensions. So first one is the origin. We know this is the origin. The second one will be at a distance of 60 inches. The third one will be the distance of 120 inches, and the fourth one will be at a distance of 240 inches. Okay, so now this has been done. Now we try to create lines to make it a structure. These lines must be straight lines from this to this, this to this, and this to 3 to 4. And we will apply, and here we have these lines. Now we'll try to make it one single entity by trying to mesh it. So when you go for meshing, you go for size controls, manual size. Okay, so now because the beam is like 240 inches, we can safely assume that maybe the length of each element is like 3 inches. And we select it. Now basically let's mesh it. And you can see the element has been generated, a single element complete for the beam. Now we shall be going for the loads. Let's apply the loads. Apply structural displacement on the key points. If you look at the key points, we have the roller at this side. You can see it becomes yellow. We apply, and the ruler will not allow displacement along the y-axis, where it will allow displacement along the x, and rotation x, y, z are not going to be constrained. And we'll say we'll apply it, and you can see it has been applied. Now we'll apply the fixed support, and we will say that it's all degrees of freedom. We'll say it's 0. You can put as optional the value of 0 because it's all automatically understood. So you can see this has been done. And now we will basically be going towards the force. And if you look at the force value, it will be our moment value is basically 10 pounds each. So the force value can be applied. You can say plot the respective key points, and say this is the point we apply it. You can see this is about the movement will be about, because truly movement will be about the z-axis and z, and it's clockwise. So we write it as -10, and that is done. You can see it's here. Now we will be basically going for uh, the UDL. And this is the UDL. So for the UDL, it's not going to be force because it's a UDL. So we will be basically doing it's acting like a pressure. And that pressure will be applied on the beams. So what we will do, we try to create a box. If you can look at very meticulously, you have to select this box, and I hope we have selected it, and we will apply. This load key 1 is for the x-axis that we wanted, and the moment to be effect about the z-axis, the pressure to be on about the y-axis. So we'll put it as 3 pounds each. And you can see it has been done. You can see it's let us fit it, and if I want it further, I can have my elements and see this has been done now. Now let the pre-processing has been completed. Now we shall be going for the solution. The pressure has been applied, you can see. Now we go for the solution, and we shall be solving the current road steps for this problem of our. It's been done. So these are all being the results being generated. Now the solution phase has been done, and now we move to the very important and real phase of deform shape. You can say that the deform shape and undeformed. Okay, so this is the result, and we can see the most important thing has been asked is the deflection of this airplane wing. It's coming out to be 0.938497 of an inch. It's not even 1 inch. So the design has been very accurately modeled, and this is the deflection that has generated as a result of our analysis and the results being shown by Ansys. So let's proceed further and try to see what results can we see for the contour plots that will be generated. Okay, so we can say that we click this button and we can basically see various results for the nodal solution if you want to, and for these nodal solutions the results that can come is basically for the displacement. We can say the y component displacement can be generated. You can see this is the displacement for the y component. We can further go along and we can see what is the displacement vector sum that will be generated. You can say this is the displacement vector sum. Then we can also go for the rotations generated. This is displacement rotation vector sum, and z component of rotations. These are the, because of the moment, these are the z component of rotation, and this is basically 0.011965 radians. Okay, this is 0.011965 radians. You can see the combined effect of all the rotation about x, y, and z. That will be this. This is the combined effect about the three moments mx, my, and mz. Okay, it's basically even smaller point because the combined effect 0.012013 radians. Now this has been done by us. Now we can see various results that you will incorporate into your final report of your complex engineering problem. So if we basically go, we can list results and we can ask for the model solutions. Develop solutions, you can say here it is. These are all the results that you could, important results you can input into the file. Not all, because it will be a very huge number of pages will be used for that. Ux, displacement in x, displacement in y, displacement in z as a result of the loads. This is the U sum, the resultant effect of all these three displacements. You can see the nodes being generated by the software, and these are the displacements, those critical nodes. Okay, so this has been done, and if you can see, you can also see if I draw the elements, you can see the nodes. These are the nodes of the beam. Okay, if we are interested in the elements, so again we can see more nodal solutions. You can see the rotation vector sums apply. You can see these are all the rotations x, y, and main rotation will be about the z-axis. X and y is 0, because the moment is about the z. Very important information, and you can basically go for the stresses if it is asked for. It can be various stresses could be generated. If we have it here, not here right now, we can basically close it down, and we can basically go for other data. We can see the reactions, the pin support, and the uh, cantilever. Sorry, and the fixed support will have three reactions. It can give you reactions as well. Reaction solutions. You want all the reactions at once. Here it is. These are reactions node 1, fx, fy, fz, mx, and y, mz. These are the this is fy. These are the reactions being generated as a result of the UDL. And these, since the moment is applied, these are the respective moments. So we have done this. Now what we can do is basically we shall be interested in what will be the shear force and bending moment diagrams. So as you know, from the previous numerical, I've also told you that there are call signs of the software that you have to call. Then define table, and you will basically add it up. You will say by sequence number, and you will be giving the call signs for 6, and you'll be applying it. And then the second call sign for will be the 19, and you'll be applying it. And then the third call sign will be for the 3, and then the fourth sign will be 16. Okay, so you can see these are the signs, and remember the call sign SMIS 6 and 19 will be for the shear force diagram, which will be about the y-axis SFY. And remember the 3 and 16 call signs will be for the bending moment about the diagram about the z-axis. Okay, and if you want, you can have the bending stresses also, because it's a beam. You can have it as 32, and then you can also have for the 37. Okay, and here it is. Rotate it, and you can close it. Now let's see how the Ansys shows us these output results. Okay, remember the first one will be for the 6 and 19 now. 6 and 19. So this is for the shear force diagram, and these are the values that have come. The maximum value is this. Then you go for the other one, which is the bending moment diagram, 3 and 16, and you will be wanting to see what is this 3 and 16, the bending moment about the z-axis. You can see this is the bending moment diagram. This is the highest value, so it is peaked. Okay, and basically this is the highest value, 11,676.1 in the negative, so it's minus. Okay, this higher value will be somewhere here at the top. Okay, and further we can go for is to see the bending stresses here, 32 and 37. And let's go for the bending stresses, and these are our the bending stresses generated as a result of this. The maximum red one is this value. Okay, so now this has been also done. Now basically we can again plot our elements, and basically now once this is done, let's see how our beam is basically plot controls. You will go for the styling, size and shape, and you will say display elements, and here it is, and you can say plot controls. Let's see the isometric view. So this is the isometric view of our beam. It's a long beam. You can see this is the beam, and so it's been properly meshed. If you look at it, and this is very important, the vertical depth and the horizontal. So now this has been done. You can say for the fit, and you can see the various results over here also, like the deformed shape and the undeformed shape of this beam. You can see this is the undeformed shape beam, 0.95 of an inch. Okay, is being there. Then you can also see the element solutions generated uh, on this beam. If you want, you can see the von Mises. This is the von Mises stress, the most important stress of your project. This is the von Mises. And what is the value? 7784 is the value. 7784 uh, pounds per inch square. But if you look at your actual failure value, or if you look for the yield strength, it is 37 psi, which means 37 value will be 37 KSI, 37,000. Okay, this is the value for the yield strength. Okay, pounds, 37,000 pounds. And what was the modulus of elasticity? It was 10 to 10 and 10 to the power 6 KSI. Okay, and this value was basically 37,000. Okay, it means, and the value that we have uh, over here is basically 7784, which means it is much lower than the yield of the material, the yield stress of the material. So the von Mises stress is telling us that it is safer. Our design is safe for the values that we have been governed up with for these values. Again, this is, I have changed this numerical so that our beam is safe. Okay, because we have added this new movement over here, and this value has been changed for the safety of the beam. Otherwise, our beam would have failed. So with the actual values of 30 pounds per inch and 10 pounds per inch. Okay, so this is being done now, and you can see as many values as you want. Okay, you can for this, if you want, this is the x component of the stress. Okay, then if you want, you can also see the principal stresses, the most important first principal stress of the structure. You can see this is the first principal stress, the maximum stress. And if you want, third principal stress could also be seen. Okay, this is the third principal stress is being shown to you over here. In the same way, you can see all these values. You can, and I have told you in my previous, if you can basically uh, go to, if you want these images, you can basically uh, take these images if you want. Uh, you can capture any of these images like this, and you can basically save it for your printing. You can save it for your future use. So this has been done. Now again, if you want any of this thing, like this is the contour plot, and you are basically interested in the von Mises, okay, and you want to see basically how, if you can say, you want to animate those results of yours. Okay, if you want, you can basically do that also. As I told you, just animate the results, deformed results. And if you want to see, this is stress, and if you look, you go down, you will see the von Mises. This is the von Mises, and you can see how results are being generated. You can also make it like this, just to see results more clearly. Okay, so you go plot control, and you basically animate it, deform results, and any results you can do it. That's not a big deal. So here it is. You can see. So this has been done just to let you know. And then, as I told you before, you also have the option to generate your own reports if you want to. And one more thing that I forgot is that always remember this images will take a lot of your printer color. So I have already told you that if you go to your plot controls and you write meta file and you write this, it will basically, you can give it anything you want to on your desktop if you want or anywhere. So you'll be getting uh, the image. If you want, you'll be getting a standard image. Here, if we have it somewhere, this is an old image, but just want to tell you the background. This will be the background image, and your beam will be there. So a lot of less tone will be used. So just from the software, your printer toner saving point of view, I'm telling you this advice. Okay, and in the end, if you are basically interested, uh, different things you can do. You can, if you're wanting, you can put your title here and you plot, and your title can come over here. This is a title, and if you want again basically you want your report to be generated, I've already told you this is the report generation, so you can overwrite it all. Okay, now this is there. You want any images, this will be your image 1. Okay, and if you want, you can basically hit it. Okay, and basically you can want to upload, you want deformed shape over here. This comes with deformed shape. You can take this image. Okay, then if you want your first principle stress, or you can see you want to start it interested in basically uh, the nodal solutions, if it is there, rotation vector sum. Okay, this is the rotation vector sum. You want this image. This, you can just add on keeping your images. It will come. Now, if you want any animation to for your results, like a deformed shape animation, if you want, so it will save that animation for you also. If it is you are sending this report to someone, and after that, if you want any tables to be given up by there to be shown in the report, it will show you the tables. You can okay, and you can say write out so the tables will be there, and then basically any boundary conditions. Okay, this table has been done, and once this has been done, just to let you know, so that you can press this, and this will become, and then report heading will be there, the title, okay, whatever the title is there. Okay, layers. This is like CP and your name, ABC, and your company and anything like that. You can put it over here. So this will be there. Okay, and then basically you can put any insert any image from outside. If you have the HTML file from outside, dynamic data from outside, these images can be added up. This image can be added up. Whatever images that you have, you can just add it up here. And like if you have tables, you can add those tables, and then this is being done, and then finally you can see your entire report over here done by the Ansys. You can see this is all being done in these tables and everything. So this is all about, again, this, remember this problem was basically a statically indeterminate problem with four, it was being constrained on, it has four constraints, three boundary conditions and one unknowns. And one very important thing, this has been done, everything is done. If you want to have some changes and you made a mistake, remember you can always go to this session editor. Okay, you can go to the session editor and you can make whatever changes that you have done. You can basically change those things and update them, save them. And for example, I can let you know, like for example, if we have we go there at the bottom and we can see this is the moment being applied, and like this ex is the modulus of elasticity. Okay, this is 10 e to the power 6. You can always make changes here, And if I say you want to make this beam as a steel beam, the steel beam A1936, okay, and you want your modulus of elasticity to be 29 10 to 3 ksi, okay, you can just change it here also. Just go to the session editor, and here it is already, I think. Go to the session editor, and you can write it as whatever it was, 29. You can make it 29 E6. You can make it 29 E6 over here, and you basically need to save it, and you can make it okay. So it will basically be doing all those updates for that. Okay, you can basically save it, and you can get here you have save it, and you can get all the respective updates. You see, and this is basically just to let you know. Okay, so this is all about this session editor will always help you a lot. And the most important thing is that you can see previously the deflection coming was, if you go to the general post processor, and you will see the deflections over here. You can see. So now if you look from here, okay, this is the deflections that is now it has been showing you over here is coming out to be it is coming out to be 0.32362. Again, first it was zero point 0.9 of an inch, now it is 0.3262 of an inch. Why? Because steel is more stiffer than aluminum, so it is going to reduce the uh, deflections. I hope you understood this problem. It will have provided you enough information for your all future projects. And I thank you all. You have a wonderful day. Thanks from my side.